Looks like we're in now.
Recording is on.
That was fast. I've had that happen before, but yeah, it'd be nice if it just automatically started, but you have to keep trying. So anyway, we're good.
I'll just wait another minute or two.
It's okay. It gives me time to reschedule all of my vaccine appointments for tomorrow and Friday because I didn't get my vaccines like I was supposed to. So, Going to make a lot of people happy because Pfizer is available again. So
I thought Pfizer was being frowned upon for the third dose.
No, not frowned upon, but just reserved for the over 30 and over crowd. Sorry, other way around. Reserved for 29 and under, so 12 to 29, basically. I don't know actually what the rationale for that is, to be honest with you. I think I came across it somewhere, but yeah, they want Moderna for 30 plus and Pfizer under 30.
Well, we got ours, our first and second doses. Our first and second doses were Pfizer, and likewise the third one, which we got on December 18th. So it seems to be they gave you choice actually of Pfizer or Moderna, depending on what you wanted. Yeah,
well, for the first time, I was supposed to get both brands in the same day yesterday, but then I got a memo in the afternoon saying, "Sorry, not today. See you on Friday." So
does that come right from the Ministry of Health?
I believe the public health units are the ones that actually distribute, if I'm not mistaken. But I mean, really, it comes through McKesson Canada, a wholesale distribution system. So, but yeah, I don't know. A good question. I think like the public health units are involved with the mechanics of it, but the physical vaccines, like I said, come from, I guess, a ministry warehouse to the pharmaceutical distributors and then out to the pharmacies.
Did you hear the new nickname for that Serbian tennis player?
Yeah.
Novak Djokovic.
Yeah.
I'm surprised the Australians didn't. I thought they had a very conservative government, so I'm a little surprised.
I can't see too many companies wanting to associate with him in the future.
Oh, he cost himself a lot of money. Can you imagine the deals?
Yeah.
Oh.
Okay. It looks like you won't be able to go to the Paris Open either, French Open.
Poor baby.
Well, the Chinese will let him come in.
Okay, I guess we should get started. Excuse me. Well, good evening, everybody, and glad to see everybody out today. And I guess they dug through the snow. Of course, we're all inside the house, so maybe you didn't even leave, left the driveways alone. Okay, tonight we have a couple of presentations. Michael was kind enough to learn about Smith charts and is going to tell us all he knows on Smith charts, and then after that we'll have a short presentation on my experiences of milling PCBs. So, and if anybody else has anything else they would like to talk about tonight, don't hesitate to hold your hand up, let me know, and then we'll go from there. Okay, you just about ready there, Michael?
Oh, I'm ready to go. Yeah. Okay, ready to try again. Put it that way. Okay, so I'm gonna share the screen. Share the entire screen. And well, that didn't work. Yes, it did. Wait a minute. Okay. Sorry, let's try again. Sorry, hang on a minute.
Oh, you were there.
Okay, let's go. So I go share the screen. I go to the PowerPoint present. No, I guess I go to share the entire screen. Okay. And now you should be looking at the PowerPoint presentation, right?
Yep.
And you should be looking at full screen.
There we go. You're all set to go.
All right. Okay. So anyway, and that should be the second slide, right? That's the second.
Yes.
Okay, good. So anyway, going to talk a little bit about, get into the weeds here. This is really my first exposure that I remember to Smith charts. I got all the, I've looked at a lot of stuff on the web, namely Al Wilkie's W2AW's presentations on Smith charts are very good. And I have shamelessly plagiarized the images from a couple of his presentations. He had said it was fine to actually show his YouTube presentation, but it's better not to, I think. But anyway, I used his stuff, and there's a couple other papers out there that explain Smith charts, so I sort of put things together. But anyways, I'm going to talk some basic concepts and then talk about an example with a load. Then talk about the other thing you can do is with cable length measurement, which I've done, and look at input impedance of a transmission line connected to a load was the other thing you can do. And there's this program called SimSmith that is an online thing you can use as well. And I actually tried that as well. So that's sort of what I'm going to talk about. Yeah. So what's a Smith chart then? What it is, it's a graphical method of displaying transmission line, to present and analyze and solve transmission line problems. And it's used to plot complex impedances, resistance and reactance, complex reflection coefficients, analyze some transmission line effects, develop matching networks where you match a load to a transmission line, and so on. And
just excuse me for a second.
Sure, yeah.
There seems to be some feedback or something, as if somebody's got their mic open or something. I find the audio is a little broken up.
Still there?
Everybody.
I can hear some stuff in the background. I don't know where it's coming from.
Yeah,
everybody probably should be on mute.
Can mute their mic, please. Okay. All right, try.
Okay. Is that better?
Actually, it is. Yes.
All right. Okay. So anyway, what it's about really is taking a pretty complicated transmission line problem and converting it to this graphical device, this process, the Smith chart. So to start at the beginning, the diagram up here is a transmission line. This is a transmission line. It'll transmit a load. Could be an antenna, let's say. I think the example I'm using, the little circuit I built, is actually pretty close to some kind of quarter wave vertical antenna. So there's your load, be it an antenna or whatever. And here's your transmission line, RG213 or RG8. The transmission line has a characteristic impedance known as Z0. And you can determine this reflection coefficient, and this has to do with if you send a signal like an impulse down a transmission line, goes down to the end, the incident wave, voltage wave goes down to the end. If the load matches the characteristic impedance of the transmission line, it just gets absorbed and there's no reflection. But if it's not matched, you get a reflected wave, and that's where the standing waves come from. At any point in the transmission line, you've got a combination of an incident wave and a reflected wave, and that gets used to the standing wave ratio we talk about. But there's this characteristic called the reflection coefficient, which is the ratio of the the ratio of the reflected voltage to the incident voltage, and you can measure that at any point, theoretically anyway, in the line. So if you want to calculate an impedance at a point on the transmission line with a load connected to it, this is the formula you use. It's pretty complicated. It's got the load impedance, the source, the characteristic impedance. It's got this tangent of the electrical length of the line in it, and this gets really messy to calculate and difficult to plot on. If you use sort of rectangular coordinate paper, difficult to plot. So the reflection coefficient is, like I said, the ratio of these voltages. And when you look at it, it comes, when you calculate this, you can show that it's this ratio of ZL minus Z0 divided by ZL plus Z0. And you can take this as a complex number. So it's got a real component and an imaginary component. So the real component is on the x-axis of a normal, if you're plotting an impedance, the real component is on the x-axis and the imaginary component is on the vertical axis. Anyway, it's got a real and imaginary component, so it's a complex number. And what you can do with a Smith chart, let's get rid of this thing here. Can I get rid of that? Hang on a minute, I can't move it. Okay, so what you do with on a Smith chart is you plot the complex reflection coefficient. And when you do that, the resistance and reactance values end up being circles, basically. The resistance in a Smith chart shows up as a circle, and reactances show up as arcs in the Smith chart. So let's just go on here. That didn't work. All right. Why can't I go on here? What happened here? I'm going to have to stop sharing and start over here. Sorry. Escape. Sorry about this. I don't know what's going on here. Just let me try this again. Where's the share screen? There's share screen. There's the entire screen. Okay, you should be able to let know right now. So you can see that? Is that okay?
Yeah, we can see it.
Okay, so the concept is that you start with the rectangular coordinates, which the typical stuff you look at here with positive R, the resistance axis horizontal, so positive resistance is on the right, negative resistance we just ignore because it's a passive circuit. Positive reactance, in other words, inductance up here and the capacitance down here. So if you want to plot an impedance, Z, it's R plus JX, so the resistance on the horizontal plus the reactance up the imaginary axis. So, and the horizontal line is a constant reactance and the vertical line is a constant admittance. So if you think about this, and what you do basically is you take this positive x-axis and you bend it over to the right. Sort of imagine bending it over to the right, and likewise the negative reactance axis, the capacitance side, bending over to the right. And then you end up with conceptually anyway, you end up with the axis being bent, so you end up with a circle. Another way to look at this is there's the real resistance axis resistance. It maps into a horizontal line on a Smith chart. The positive reactance maps into a semicircle starting at the extreme left here and going around to the right, and likewise a capacitive reactance is on the bottom. And the thing about this is when you look at this, the circles are constant resistance circles. So these represent different resistances. This one would be the the resistance going through the origin, and everything is scale. I'll come back to that in a minute. And these ones are greater than the characteristic impedance. These ones are less. So you get circles coming out here, and these are reactance arcs. So when it comes to look at plotting a resistance and reactance, what you do is you find the appropriate resistance circle. Where's my mouse? So here, let's say, and then you find if it's inductive reactance, you look for the arc that represents that reactance, and it would be, say, right here, and that's where the impedance would be mapped on a Smith chart. So So you can do an admittance thing as well. Admittance is the reciprocal of an impedance. So it's, instead of being Z is R plus JX, it's Y equals G plus JB, and G is the conductance as opposed to the resistance, and B is the susceptance as opposed to the reactance. So you can do the same thing. It's on the other side. It's on the left-hand, both circles end up on the left-hand side of the Smith chart. So basically, when you're looking at the Smith chart, you're looking at the reflection coefficient, only it's not shown directly on the chart, but that's really what you're looking at. So here is, there's the inductive portion is here, the capacitive portion is here. This is purely resistive here. So there's no impedance on the horizontal line here. The other interesting thing to think about, look at in the Smith chart is, if you start with an impedance someplace, let's say here, and you go a half wavelength down the transmission line towards if you've got a load connected to a transmission line, if you go half a wavelength down that transmission line, the impedance travels around the circle and ends up back here half a wavelength later. It's back where it started. And on the outside of the Smith chart are scales showing you how far around wavelength, this is wavelengths towards the load, I think it is, or towards the generator, I forget now. So there's a lot of stuff in the Smith chart, useful stuff. So, like I said, these are the resistance circles. This would be, and this is a normalized resistance. Basically you take your impedance, whatever it happens to be, and you divide it by the, which would be, let's say 50 plus J 30 ohms, you divide it by the characteristic impedance of your transmissions, of your system, which would be 50 ohms, let's say. So instead of being 50, it's 1, because 50 ohms divided by the characteristic impedance is 1. So that would show up right here. So when you plot things, you normalize them first on the Smith, oops, sorry. You normalize them first on the Smith chart. Come on here, come on. Sorry about that. So here's the constant reactance arcs, and these are normalized as well. So if your reactance had been 50 ohms and it was an inductive reactance, then that would show somewhere on this arc, because this is the 1 ohm impedance arc, and up here in the top, these things are labeled, so it'll be labeled 1 up here. Likewise, this would be -1 down here, and -0.5 and whatnot. And over here, there's no reactance. On this line, there's no reactance. So those are the constant reactance arcs. So when you look at a Smith chart, there's some key values. An open circuit on a transmission line is an infinite resistance at the end. So it shows up here. A short circuit would show up on the other side of the circle, and in here, this is the characteristic impedance Z0. One of the things about Smith charts is that constant standing wave ratios, or constant standing wave ratios, show up at reflection coefficients, which is the same thing, show up as circles on the Smith charts of different sizes, which is handy when you're looking at figuring out what standing wave ratios are. There's a couple different types of Smith charts. There's the impedance only one on the left, which just shows the resistance circles and the reactance ones. Excuse me. Then there's the other one on the right, which shows both the impedance stuff is shown in red. So the constant resistance circles are here, and the constant reactance arcs are in here, and likewise down the bottom. Also on this Smith chart is the conductance circles, and the blue circles are the constant conductance. Sorry, admittance is what I meant. The blue circles are the constant conductance, and the blue arcs are the constants and susceptance. So you get both on the same chart, which is handy when you come to plot when you do matching. So what I did, and this is based on Al Wokie's stuff, I took a 33 ohm resistor, connected it in series with a 220 picofarad capacitor, and that was my load. And that's, of course, a SMA connector, soldered it to the SMA connector. So you plot it on the Smith chart. So how you do it, like I said, it's normalized. So the load impedance is R plus JXC, which is R plus 1 over J plus J times 1 over times minus 1 divided by 2 pi FC. So going through that calculation, if your capacitance is 220 picofarads, that makes it, where is it, minus 51 ohms. And the resistance is 33 ohms. So that's the nominal value. And when I actually measured what I had, I got 32.43 and 224 picofarads by my measurements. So it's a little bit off. Anyhow, you take the load impedance, this 33 minus J51, and you normalize it to the characteristic impedance, which we're using 50 ohms here. So that becomes the all is divided by 50, which is 0.66 minus J1.02. And there's no units associated with that. And that's what you plot on the Smith chart, is the normalized value. And it's at the constant, it's at the intersection of the constant R circle and the constant X arc. So, and likewise, you can read from the chart, having plotted that, the impedance, you can actually read the admittance right off the chart as well, just by using the other circles in different scales. So this is plotting the 33 minus J51, and this is on, I've got this just to show you, this is on the constant resistance circle. It's, whoops, yeah, let me back up. Okay, I can show you this. This is it's on the constant resistance circle here, which is the 0.66 resistance circle. And the reactance is minus 1.02, so it's on the minus 1 reactance circle here. And that's where the load impedance is. And just to go back, it's here on the chart. And this is just, the next one is just a portion of the chart so you can see better. And down the bottom of the chart here, by the way, is a bunch of scales, and you can read the standing wave ratio right off the scale here. And how you do that, let me go back here. You basically draw an arrow from the origin, the Z0 point, the R equals 1 point right here. But it comes down to the impedance here, and then you rotate that around to the left-hand side here on the horizontal axis, and you drop a perpendicular down here, and lo and behold, the standing wave ratio is right there. Very handy. So what you would do is you take this is the horizontal line here, and when you drop this down to the scale below, you can see a whole bunch of stuff, including standing wave ratio. So that's how you go about plotting an impedance. So the other thing you can do with the Smith chart is you can, if you know what the length of a cable is, you can predict what the source impedance at the open end of the cable is going to, or where the source would be on the cable. So what I did, I took a piece of RG8U, which was 30.3 feet long. I measured it with a tape measure, so I knew it was 30.3 feet. That's 9.24 meters. Then what I did, I used the Nano Vna. There's a function in the Nano Vna that you can use. You can use what's called a transform function, and it'll measure the length of a cable for you. So what the transform function does basically is it sends, having set it up, it sends an impulse signal, like a pulse, down the transmission line from the VNA, and measures it when it comes back, and it measures the transit time, and from that it calculates the length. And you can see here the length, lo and behold, is 9.24 meters, which is exactly what it should have been. One of the things you put into this thing is the velocity factor. And RG8U is supposed to have a velocity factor of 0.78. But when you put in 0.78, you get the wrong length. So I fiddled around, and if you adjust the velocity factor to 0.74, it works. And the velocity factor is the speed of light in the cable relative to the speed of light in a vacuum. So that works, and it gives you right on the Nano Vna, tells you the length right there. All very handy. So what I did, I measured my cable at 9.24 meters, then I calculated it with the Nano Vna. And then you go through this process. I'm using a frequency of, I forgot to mention, the frequency I'm using is 14.200, which is why it's 51 ohms for the capacitive side of the load. So the wavelength for 14.200 megahertz is, one wavelength is in free space is 300 divided by the frequency, which is 21.13 meters. In the cable, you take that 21.13 and multiply it by the velocity factor, and that's the one wavelength, electrical wavelength in the cable, and that's less, so it's 15.63. So that means the cable length in wavelengths is 9.24 divided by 15.62, in other words, 0.591. So now what you do is you take your load impedance, which we already plotted on the Smith chart, and you go from the load impedance, you go round the constant resistance circle, 0.591 wavelengths. Well, one rotation is half a wavelength, so you go up, you go complete. Sorry, is that me?
I think so, yes.
What's going on? Okay, you take, basically you move right around the chart. It takes you half wavelength around the chart. This is 0.591, so your impedance, your input impedance is going to be a little bit more. It's going to be 0.091 wavelengths further around the chart than the half. And I mentioned earlier the actual impedance I was using is a bit different from the nominal I was talking about earlier. So I did this on the chart, and then I measured it with the Nano Vna. Tells you when it looks at the combination of the cable and the impedance. It tells you what the resistance and capacitance is, and it comes out pretty close, because this is what it's supposed to be calculated out, and this is what the Nano Vna tells you. So it's pretty close to what is on the chart. So here's the chart. This is what we started with, was the actual impedance I had, the 0.648 minus J1, and the wavelength is 0.591. So it's one complete rotation around this constant SWR circle all the way around. That's one half a wavelength, and you add 0.091, and that means that's where the input impedance of the cable plus load combination is, and that's the 0.34 minus J.29, which is works out to be very close to what the Nano Vna calculates it to be. So that's how you use the Smith chart to come up with the impedance of the input impedance of a cable of whatever length, given you put a load on the end. So another thing you can do with Smith charts is you can match an impedance. So when you look at the Smith chart, so basically you pick up a particular network topology. It can be capacitor in series, inductor in parallel, or any combination thereof. You pick the particular, some of these are, this is the sort of allowed region for doing this kind of stuff. This is a forbidden region. This stuff doesn't work out here. So basically what you do is you start with your load and you match to the source. Well, if the source is, you want to match it to 50 plus J0, like resistance, no reactance. You want to make it 50 ohms. So what you do is, if you're going to use this particular topology, which is a parallel inductance and a series capacitor, you can end up with the input impedance looking at 50 plus J0. And when you look at navigating on the Smith chart, if you have a load and you have a series inductance, you move this way clockwise on the positive side of the chart. If it's a series capacitor, you go counterclockwise. That's the way the impedance moves on the chart. A parallel inductance, this is on the resistance and reactance part of the chart. If you go with parallel inductances and capacitors, you're dealing with the conductance side of the admittance side, in other words, the left-hand side of the circle, excuse me, of the diagram. So what you do is you start with your load wherever it happens to be. We want to add an inductor in this case, so we want to move along a constant conductance circle on the chart. Because an inductance has no conductance, it's just purely reactance or susceptance. And when you add a series capacitor, it means moving along a constant resistance curve on the Smith chart. So the first thing you do is you start, you add enough inductance. I'm actually going to go to the chart. It's easier to show you the chart. So basically, the load is down here. And what you want to do, it's the 0.66 minus J1.02. And what you do is you add enough inductance in parallel with your load to take you to the R equals 1 resistance circle, this one here. That's the first step. And then the second step, having done that and calculated what this inductance is, you then add a series capacitor, which moves you along. You need to add enough series capacitance to move from this point, oops, sorry. Yeah, from this point here, which is the R equals 1 circle, to the no reactance part of that circle, the origin, basically. So we started down here where our load was, and we are moving along these constant conductance circles. And what you're doing is you're calculating the inductance you need to move from this point to this point. And the first thing you do is you calculate the susceptance involved, the change in susceptance on the admittance circle to get from the load up to this point on the R equals 1. And that worked out to be 1.19 in units. And then having done that, you then calculate from the chart how much capacitance you have to move, and you get that from the capacitance arc for this point to down here. So that gets you a 1.1 in terms of the arc. So I'm just going to go back here. Okay, so back up here. When you did that, you go through this calculation. It tells you that you need this change in susceptance here. The 1.19 translates to an inductance at 14.2 megahertz of 473 nanohenries. And the capacitor is, I think it was 220. So yeah, so what I did, yeah, so basically the calculation shows it's 473 or 471 nanohenries. And the capacitance should be 204 picofarads. And that gets you from the load point to the matched position on the Smith chart. And when you calculate that, you actually come out, you go through the calculation, you put the numbers into the Smith chart, and when you actually look at it, it's not quite right. It's 53.5 versus 50. And 1.72 versus 0. It's close. So what I did, I built a test circuit here that basically consists of an inductor inductor in parallel, and I actually built one. And the closest I get to 473 or 471, which is the ideal value, is 484, 8 turns on an 80-6 core. And the capacitor, I couldn't get the exact capacitor value, but it came out pretty close. So there's the test circuit right here with the load on the right-hand side. There's the parallel inductance to ground, between this point and ground. And here's the series capacitor. So I put a couple together. So when you connect, when you look at this on the Nano Vna, it comes out to pretty close to 50 plus J0. And that's what this is showing. This is a, you can get with the Nano Vna, there's a program called Nano Vna Saver that plots on your laptop or whatever what the Nano Vna is showing. So here's the Smith chart the Nano Vna shows. And you can see there's the resulting impedance is right here, having matched things up. And it tells you, this thing tells you 53.5 minus J1.72. So it's not quite right, but it's close enough to make the point. So that's sort of how you do it. That's what the circuit looks like on the test board that I built. Fortunately, I happen to have an 80-6 core. I have a whole bunch of 3743s, but the inductance, the number of turns is like 0.1 or something on that, so it's hopeless. You can't do it, so use a different core. There's this program called SimSmith that I talked about, and this is pretty well the end. It's got a Smith chart, and you run this on a laptop or whatever, and when you turn it on, it shows a source. This is the source here, and it shows a load here, the green. And what you can do, you can take components and add it to this circuit. You just drag them up, and then you pick the values on the diagram. So this is what you do here. So you start, there's the source, there's the load. So the first thing you do, that diagram before just basically showed the load and the source. So what you do is you drag out your parallel inductance here, and just plop it in here, and now you've got the load, the parallel inductance, and the generator. And that looks, when you do that, the diagram, if that's all you saw, you'd see the impedance move from here up to here. And this is the changes in susceptance we were talking about earlier that you actually pull right off the chart if you're doing it by hand, off a real Smith chart, as opposed to this. Having done that, then what you do, you're going to put a series capacitor in now. So you take your capacitor image here and you drag it up in here, and then you pick the values of these components because you know what you're doing. So you pick there's the 484 nanofarads that I could actually build, and there's the where's my mouse? There's the 204 picofarad series capacitor. And having done that, it shows you're almost on this faint red line here is the constant resistance, the 50 ohm resistance, the circle. This is the R equals 1. The SimSmith works in actual values, not normalized values. So you can see there it says 50. So I'm a little bit off and a little bit down. Anyway, that's pretty well what I have to say. That's all I know. And I presume there must be tons more you can do with this, but that's what I know about. There's another example. Oh yeah, this is the last thing. This is an example I found in a magazine, in an article somewhere. Basically, there was the load, a parallel inductance, a series capacitance, a parallel capacitor, a series inductance, and the question was, well, what are these values? And they gave the susceptance values. I forget now exactly, but basically, you put them in one by one, and it shows this pattern that it starts here. Well, they're color matched. The parallel inductance moves you that way. The series capacitance comes down here. The parallel capacitance moves you along a conductance circle, and then the series inductance moves you up this way. So that's how you use it. And they also have it down the bottom here, someplace they have a transmission line model too. I can't see it offhand, but it's here someplace. Anyway, so there's different things you can do with this. Anyway, that's what I run out of things to say. So there's the references. Al Wilkie's got a very good presentation. It's a video on the basic of Smith charts, and you can actually look at the PDF files. And I use that, and also his other ones on the other shorter videos on the various different things. And he has one on measuring coaxial cable length, and there's a tutorial on impedance matching that I used, and there's this other paper this CERN scientist, on basic concepts. So yeah, so that's where I am. That's what I found out. So what'd they do? Oh. So yeah. Sorry, yeah. So there, I'm done.
Okay, well, thanks, Michael. That's
I don't know how coherent that is, but anyway.
the Smith chart. I think you've shown me why the Smith chart looks complicated. I think I have a few cheat sheets with me to go through that. But that was certainly a good introduction. It looks like there's a ton of information that can be derived from using the Smith chart. One thing I did notice, I was going to mention, when you're talking about velocity factors, when I was messing around a little bit with measuring the speed of light and all that kind of stuff, I noticed that for the same cable or the same piece of coax from different manufacturers had different velocity factors. So maybe the cable you had a different velocity factor because of the manufacturer. Because originally I thought, for example, all RG213 had the same velocity factor, but that's not quite true.
Well, I started out thinking I was using RG213, and RG213 is supposed to have a 0.66 velocity factor, and when I checked it, it was 0.74. Well, what's going on here? And it took me a while. I was talking to Daniel about it, and Daniel and I about it, and it took me a while to figure out that what I actually had was a piece of RG8U, which of course has a different velocity factor.
Yeah.
But yeah, the standard velocity factor is supposedly 0.78, but when you look at it, it's got a tolerance. So even, you wouldn't expect it necessarily to be exactly 0.78, and 0.74 is within 5% or something.
Mm-hmm.
So yeah, and presumably if I picked up another piece of RG8U, like you say, I might have got a different value.
Yeah, I can't remember the difference between the manufacturers now. It was too long ago, but there was a difference, that's for sure. Dave, you had a question or a comment for Michael?
Yeah, just on that whole thing of velocity factor. Tiny bit of experience in FM broadcast arrays. When you order like a 4-bay dipole antenna, which is the most bang for your buck in FM broadcasting, and it's very, very popular, they specify that the jumpers from the power splitter to each dipole must be from the same spool of coax. And if you're going quasi omnidirectional, they must be exactly the same length. They must be identical. You can't, even from the same manufacturer, they won't take 2 jumpers from one spool and 2 jumpers from another spool. It's got to be all off the same spool of coax. And I've had just a little bit of experience of people, the jumpers are a little bit different, and it skewed the pattern. So just emphasizing your point there that, yeah, velocity factor seems to be kind of a temperamental thing even from one spool to another, let alone one manufacturer to another.
Mm-hmm. Yeah, that's interesting. We have a 4-bay VHF antenna for our repeater, and it's got the four elements and the jumpers, and I guess that must be true. They're all the same. They have to be all the same, yeah.
Yeah, well, you can do the math and the calculations with velocity factors, and you can see you don't have to be off by much to make a difference. That's for sure.
Yeah.
Okay, is there any more comments, questions for Michael?
It was a wonderful presentation, Michael. I have an awful lot to learn.
Yeah, well, it's I started really from nothing. I knew vaguely about Smith charts. Remember vaguely or learning about them a little bit in university, but I had to look it all up. And Al Wilke's stuff is just wonderful. You know, it's all there. You look at his YouTube videos, it's all there. So, but pretty complicated stuff. What you can do with these things.
Well, it seems that I'm trying to put together a hairpin loop on a Yagi antenna, mostly Yagi, and the velocity factor plays a tremendous part in that. And I'm off probably by about an inch or an inch and a half on the length of this thing. And I think this would be a much easier way to figure out the proper length. Because yeah, I don't know the velocity factor, and you must know the velocity factor to make this work.
Yeah. Well, you can get velocity factors off for what it's worth. Maple Leaf Communications has a table of velocity factors for different coaxial cables. I'm not sure that would help you, but
well, I think about the point where, as Dave mentioned, that it's specific to the piece of coax I got in my hands. It's very finicky. If I don't get it just right, the SWR flies off.
It's trial and error then, yeah.
It is pretty much. I was trying to avoid that by actually figuring out the velocity factor and thinking I'd actually put some science behind this instead of just bashing on and hoping I got the right direction when I cut it off.
Yeah.
Can you read who's the manufacturer on the cable?
I have to redo the. I can't read the. No, no. Manufacturer is not legible.
Oh, okay.
But if you had it,
too old.
The other thing I discovered with doing this, I have this Nano Vna, and it allows you to figure out velocity factors. Like you can measure the cable and change the length and figure out exactly what you've got velocity factor wise.
Yes,
that's a neat little tool, that Nano Vna. I'm very impressed. I've had it for a while, but I haven't really used it very much until I did this stuff. Pretty impressive.
Hassan, you had a comment?
Yeah, this is the first time I've seen a Smith chart explained with actual circuit, like actual circuit inductors being wound, and with a physical demonstration. And that was a real treat.
Well, I thought that was neat. That you can actually you do this matching thing, and it shows you on the chart what you can do, and then you actually do it, and it works. And you just wind the coil, and it's I like doing that kind of stuff. I think that's neat.
It's kind of neat to try things out on the bench as well to prove the theory. Just a quick comment here. I see Jitsy's done another update to the program, and now when you put your hands up, a little yellow flag under your picture.
Oh yeah, look at that.
So that's kind of cool. Anyway, the next one up is Dave DAC.
Just a question. The Nano Vna you used, is that the smaller one, or is that the 4.3 inch screen?
I bought the H4. I bought it. I decided to buy the H4 rather than the 2.8 inch one, the original one, and I got it from R&L Electronics in the U.S. and thereby avoiding possibly getting clones off Amazon and stuff like that. There's a lot of stuff on the IO groups about excuse me, people who buy clones and have problems with them, but I've been very pleased with that. And
that's the one that's 150 or 200.
No, it's $45 US.
The H4, R&L Electronics.
Yeah, go to R&L Electronics, and it's the H4. It was $45 last time I looked, US dollars, mind you.
Yeah, that's fine.
And the other thing is, they won't ship to Canada. So what you have to do is you have to use a service like cross-border pickups, which is what I use all the time. And the way that works is you get a free mailbox in Niagara Falls, New York. You register with cross-border and you get a free mailbox. Then you have your stuff delivered to them in Niagara Falls, as opposed to you here in Canada. And it shows up in Niagara Falls. You pay the US shipping to get it there, which is a lot less than across the border. And then you pay them a fee, cross-border a fee, which is like for something like the Nano Vna, it's like $9 or for $10 or something, and it shows up in Mississauga, and the Kamado Drive in Mississauga, which is close to Sale. I don't know where you live, but it's close to Sale. And then you can either pick it up there or you can have it mailed to you in Ontario or wherever. So that's the way to get it.
So cross-border.
It's called Cross-Border Pickups, CROSSPICKUPS.ca. Crossborderpickups.ca. And if you go look at their website, it tells you all about how to use it. Basically, you get yourself the mailbox. Mine is box 3403, and basically you tell the guy you're buying the thing from, ship it to box 6403 or whatever it is in Niagara Falls, New York. Shows up there, and then they email you, Cross-Border does, they email you and they say, what's the cost of this item in US dollars? And you tell them that, and they use that to calculate GST. Basically, there's being no duty. You end up paying a GST amount on the value of the device, and then you give them your credit card, and they charge you that cost plus the cost to deliver it to Mississauga, and presumably if you get it mailed to you, the cost of the extra mailing, and then they email you when it's there. Piece of cake.
That's great, because I've got a sister that has a box in Alexandria, but you have to cross the border to get to it.
No, you don't have to do that. No, this is easy. It's really, really, you don't have to drive to Niagara Falls or whatever. You just order it that way. And yeah, I ordered a 6x6 by 20 inch box, metal box with about 20 lightning arresters in it for the club's the VA3MIS club station, and it was going to be $250 to ship it from Utah to Canada, and it was like $70 from cross-border pickups, plus the $30 to get it from Utah to Niagara Falls. So it's really worth knowing about.
Yeah. Okay.
I'll
thank
second
you.
that. I've been using them for years. Very good service.
Yeah, they're very good. Yeah.
Okay, that sounds good. Okay, we've got a few more comments coming up here. Phil, you're up next.
Yeah, I've got the small version, just the H version like that. And I have it running on with a Windows 10 machine with the Vna Saver software, and it runs just fine there.
That's what I'm using. Did you say it was the H4?
It's just the, no, it's just the H, not the H4.
It's the smaller one.
Small one, yeah.
Yeah.
But tonight, because of this, I decided to load it on this computer, which is a different computer, and it's running Windows 11. And lo and behold, it won't run. The Saver part won't run. It'll run, doesn't give any errors, but doesn't pop up either. So wondered if anybody had tried it with Windows 11.
I haven't. I'm running Windows 10. I dread going to Windows 11 if I ever have. Well, I'm going to have to do it in a few years, but not now. You might be able to find on the user group some advice.
Yeah, well, that's where I'm at the moment, and I can't find anything that says Windows 11. But apart from this, I'm running all sorts of other ham radio software on Windows 11 here, and knock on wood, I've had zero problems. They just run absolutely the same as Windows 10.
That's good. That's good news. Yeah.
Hey Phil, try running it in compatibility mode. If you right-click on the icon and you say Properties,
okay,
or you could tell it to say Run in compatibility mode,
and or maybe administrative mode.
I tried it in administrative mode, and that didn't make any difference. But I'll try it.
No, it doesn't. It's not administrative. No, you're running it in compatibility mode.
Yeah. Okay, I understand. So I'll try that. I'll try that.
You're making the application think that it's running in Windows 7 or Windows XP or Windows NT. You're tricking the application into thinking it's running in a different operating system. That's what compatibility mode does.
Oh yeah.
That's assuming that Windows 11 has compatibility mode. I see it's got troubleshoot compatibility, but
I'm almost guaranteed it's got compatibility mode.
You'd right click on the application on your desktop, and it would give you a bunch of options, one of which is compatibility mode. Isn't that right, Dave?
I know that. That's what I'm doing at the moment. It does not say run in compatibility mode. It says run it administrator, all that sort of stuff, and then it
Yeah,
says,
Phil, just Google it, man. Just go and.
well, if you don't want to listen to what I'm trying to say, don't bother then.
Okay, come on.
Sorry.
When you click on the properties of Nano Vna Saver, does it give you a list of properties?
It gives me a list of things for properties. Just a second.
Right click on it and look at properties.
Yeah, it says properties, and compatibility is one of them. Okay, it just says run compatibility troubleshooter.
Oh, interesting.
So I think that's a change in Windows 11. It doesn't have run in compatibility mode.
Huh.
So maybe I'll run the compatibility troubleshooter and see what it says.
Well, you never know.
Anyway, you guys carry on. I'll just play around with this.
Dave, you had a comment for Michael? OOI?
Yeah, Michael, could you not come back to velocity factor? Could you not get the velocity factor experimentally? If you know what the cable length is, you've got a fixed cable length. You put, you inject, like I say, a 1 megahertz signal into it. You put scope probe 1 on the front, scope probe 2 on the back end, and you trigger it so that scope probe 1 goes off. Then you'll see the signal delayed by a certain amount. And if you turn your resolution right down to like nanoseconds, you should be able to see the first pulse and then the second pulse come up. And the difference between that, it's the time it takes to go across that cable. You know, the distance, you could come up with the velocity and compare that to a speed of light, and you could get the velocity factor. Could you not do that?
I think that's exactly what the Nano Vna does. So I don't know why, because it tells you on the screen when you look at it. It tells you on the screen when you get the length. It's telling you what the transit time is. 83. I think it was 83 nanoseconds or something like that. But presumably you could do that with a scope. I'm going to try that. It's a good idea. I'm going to try it and see.
Well, actually, if you look at Alan, has got a video where he shows you how to use a scope to check the open. I think it's Alan or Dave Jones, one of them.
No, it is Al. It is
where you can see the actual reflection coming back.
That's right. I think that's right too. Yeah.
Yeah, because you'll see the reflection because it's open, so everything gets reflected back, and so it'll be twice.
Yeah.
The time will be twice, right?
I got to go have a look at that. I didn't bother with that because the Nano Vna it tells you right on the screen, but that's a good idea. The other thing is the Nano Vna Saver program has a TDR box, which is the time domain reflectometry, which is the same kind of thing, but I can't get it to work. I don't know what I'm doing wrong, but anyway, yeah, I'll have to try that and see. Be interesting to see.
Okay, Al, ALH, you got a comment? Question?
Your microphone's off.
Sorry, no. Did you have my hand up?
I thought you had your hand up. It's been a while.
No, I didn't. Just enjoying the conversation there. Well,
okay.
While I got it, thanks, Michael. I've been playing with Smith charts over the last year or two, never fully understanding. So it gave me some clarity. So thanks very much. I enjoyed that.
We should go have a look at Al Walke's stuff. The which one? 279. The first one on that list is excellent. He goes through the whole thing, and when you do that, you'll see that I plagiarized shamelessly. That's where I got my stuff. And there's a couple of other papers, and also Ward Silver did something.
I've been reading Ward Silver's work. And that's where I've been getting my materials. By the way, is that SimSmith software available online? Or is that,
it's free. Just download it. Just download it.
I'll go.
And it's got like a 400-page manual. Like it's very, very detailed. So I just sort of skimmed did what I wanted, had a look, and just it seems to work, and that's about all I know. Okay. But I don't know. What I know is what I told you. That's all I know about this stuff.
That's good. Drew, you had a comment?
No, I'm enjoying this, but this is way out of my league.
Well, I could have sworn that you had your hand up earlier. Okay.
No. I was cleaning my hand and it went off.
Oh, Dave's got a link there with something about
compatibility mode in the chat.
Yeah.
Oh yeah, I see that. Okay. Okay. Is there any more comments, questions for Michael? Hassan?
Yeah, I think I mentioned this before, but the purpose of the Smith chart, like, you could do this on a rectangular XY grid. Just have R on the x-axis and then the reactants on the other axis, the y-axis.
Yeah.
You plot your point for your Z load, you plot your Z naught, and then you want to find your source impedance. The problem is it'd be a really funny curve, which impossible to draw. The reason you use a Smith chart, if that equation you showed in the beginning, Michael, that Z equals all the arc tan H and all that, that's the key equation. The whole purpose of the Smith chart is to solve that equation graphically. So they do that transformation, and then you can just use a compass and a ruler to figure out to solve. Yeah, so if you don't want to do any of that, you could just plug it into the equation into Excel and maybe get some of the same answers.
I guess you could, yeah. I think in the university we learned about conformal transformations, and I think this is one of those that transforms the impedance plane into the reflection coefficient plane and all that stuff. Yeah. And it's magic. It's magic, but it works.
Yeah, it's the Z minus 1 over Z plus 1 conformal mapping.
Yeah.
Yeah, that's right. That's.
I vaguely remember that stuff. That's about all I remember. Too long ago.
Me too. I mean, it's simple. But in the days before calculators and computers, it was, it saved a lot of computation.
Oh yeah, it would do. Yeah.
Yeah.
I managed to successfully avoid transmission line theory in university.
Any other questions, comments? Oops.
Okay, I tried that suggestion that Dave had there, and you would think it would work, but here's what I got, and I think it's because Windows 11 has not updated that compatibility mode to Windows 11, because when you go to run this program in compatibility mode 4, and then you have the drop-down menu, it gives Windows 8, Windows 7, Windows Vista, but doesn't give Windows 10 because Windows 11 apparently doesn't realize it's Windows 11 yet. So
isn't that nice?
Isn't that nice? Yeah. Okay. Thanks for trying, then.
Okay. Any other comments, questions?
My last comment is I successfully avoided doing this presentation. It must be about a year.
Well, thank you, Michael, for putting it together. And I knew there was a bit of a learning curve there for it, but I think it was worth the wait.
Oh, it was worth doing for sure.
Yeah. Okay. And I see there's a few links and whatnot going in on in the chat there, so check the chats out before we finish tonight. Okay. Well, I guess we'll move on then. I've done a little bit with the CNC machine, and I have to just put together a few slides on what my experiences are so far. So I'll go with that. Can you see that?
Yeah.
Okay. Milling PCBs, and it's my way, not anybody else's for sure. Well, I went and bought the Saint Smart Prover 3018, which is on the upper left, and it comes mostly pre-assembled. They tell you it takes 15 minutes to build it out of the box, but that's not true. If you put several of them together, you can do it in 15 minutes, but I think I took a couple of hours anyways. Very impressed with the construction of it. It's very well made. And the cost is about $400 off of Amazon, and I think it was like a couple of days delivery. Excuse me. And at the bottom picture there is the controller that comes with it. But I've not tried the controller. I've only just used my computer to interface with the machine. You'll definitely want to buy those blue bits on the left, some more of those. That's the V bits. That's what I use for milling the PCBs. Drill bits, you'll want some different sizes. So they're $22 for that on Amazon. I think Q kits, V bits were $22. The drill bits are are easily are a nice price here. A local supplier here at Q-Kits here in Kingston. Probably don't need some of those really small ones. I did pick up the spoil board, which is this here. It's a bit pricey. And if you're doing PCBs and you weren't going to drill holes, then you probably don't need it. But the nice thing about the spoil board, it does come with some nut certs in it, so you can, if you're going to use the clamping method to your PCB down to the table, then that board's probably not too bad. But there's an issue with that too, and I'll come to that in a minute. And we want to pick up a can of dry lube as well for the worm gears. And why did I do the change? Well, for a long time I wanted to start getting away from using etchant and all the messy cleanups and that kind of stuff that was going on. But the main thing that really pushed me over the top was I started to run into trouble with the heat transfer method. I just could not get the toner to transfer properly. I'm not sure what was going on, because early on I was having really good success with the heat transfer method. I still had to repair the tracks with the Sharpie before we did the etching, but regardless, it was starting to become a pain. And of course, since I've been thinking about a CNC for a while, when I started to run into troubles, that was the time for the change. So instead of ironing the paper board on and repairing traces and all that kind of stuff, and the etching and peeling the paper and running back and forth, I now sit in front of a computer and I import Gerber files into a program called FlatCam. And in FlatCam is a program that you use to set up the different parameters for the G code. That's an example of that is the Z cut, the number of passes you want your spindle to take, the speed and the travel of that spindle. You can also set up, well, you use KiCad to set up the files for the drill hole specs, and then you'd confirm them in you'd enter that all into FlatCam. And then once you've done that, you then import the G code into Candle, a program called Candle, and that's the program you use to send the commands to the CNC machine itself. You also perform what's called a mapping function within Candle, and here's the screen for that. Basically, in this particular case here, what I did was I set up a grid of 5 by 5, and when you're doing the mapping function, the spindle will come down and touch the PCB in this particular case, 5 locations. So 1, 2, 3, 4, and 5, and 5 up this way in that kind of a grid fashion. And in here, if you can see the different numbers, that's the height that the spindle had measured. And then it'll take all those values into account so that when it's doing the milling process, you can just kind of see background here where it's going to be doing the milling. It takes these heights into account, and it works pretty well. But you can see the variances there. Some of them are not too bad, but there you can see some variances.
So Peter, what it's doing is it's drawing the traces for you and then drilling the holes?
Well, before I start, say again.
Is it with the CNC? What is it? It's taking a piece of PCB material and drawing out and cutting out the traces for you and drilling the appropriate holes for the through hole stuff. Is that what it's doing?
Yes, you can. It's a couple of different files. Like the one file will be for milling out the traces, and then there's another file that you would run to, and of course you'd have to change the bit from a milling bit to a drill bit to drill the holes. And then there's another process, and we'll cover that a little bit later, about where you would actually mill out the board out of the PCB, but we'll cover that off in a minute. So what's the disadvantage of doing it the the CNC way? Well, the cost of the CNC, I suppose, $400 would buy a lot of etching material and whatnot, I suppose, and toner. The amount of time to produce a board, well, it's quite a bit longer to mill out a board than to etch a board, for sure. There's no question about that. The only thing is, once you start the milling process, you can leave it alone. You don't have to touch it. So the board I did took, I think, around 2 hours to do, but you could be doing other things in the shack. You don't have to have hands-on once that's all done. It is a bit noisy. I mean, it's not overbearing, but it is a bit noisy, so we'll say that. May have problems with some of the really small SMD sizes. I'll go over it a little bit later on as well, but there's a way around that if it comes out to be that, and that would be the use of breakout boards. And for me, I don't find that there's no disadvantage of going to the CNC method. On the upper left, it comes with a sensor that's used in the mapping process. Now, if you're doing nothing but PCBs, then you don't really need that. That's where, you know, because the PCB on the bottom there, the picture on the bottom right, you can see where I got two clips on there. And what you're doing is on the mapping function, when the milling bit touches the PCB, it completes the circuit. And you can see where I've got this clamp here will be on the PCB. And then when this drill comes down and it makes contact, then the circuit is complete. And then the probe stops going further down. If you're going to be doing a non-metal carving or milling, then you're going to have to put this on there so you can find where the surface is, and then you have to make a measurement of the depth of this and put that into the candle program, so to take that into account. The other thing is the hold down clamps. These clamps here were what came with the CNC, and depending on the size of the board and where you're doing it, some of these holes here where you screw into for the clamps may not line up perfect, so you may need something that's a little bit longer. I was thinking maybe 3D print some clamps, but I also went on to another method, which I'll cover off in a sec, to get around that clamp issue. So some of the initial issues I had were, well, I did a total of about 27 trial runs. Probably about 23 or 24 when I finally got down to a fine, you know, to a point where I was comfortable that I could probably start producing something that I could use. One of the main problems is the way I started off. I started to try to mill really, really small, the SC70 package size, thinking that if I solve that problem first, then everything else comes easy. But the trouble is making sense of everything. I'll come into that in a minute. The initial issues, well, my setup, I have the milling machine behind me, and of course the computer screen is the opposite direction. So between looking at the computer screen and then turning around and doing something with the CNC and then back and forth, I forgot to take the sensing cable off, and you start the thing up, and of course it wraps itself up and around it. But the alligator clip kind of spins on the milling bit a little bit, so I haven't ripped anything out yet. Forget to install the sensing cable. Well, there is the fallout from that is the milling bit comes down and hits the PCB and wants to keep on going. So there goes the tip off your bit. Forget to change the Z cut depth from default. Yeah, well, that explains this big hole over here. It went way deep. So it's a good thing I had a spoil board, because I would have gone right into the aluminum table. Don't raise the spindle height enough to clear the clamp. Well, when you finish milling and then you manually bring the bit up and then swing it all out of the way in a bit of a hurry, and you're doing, like I say, the back and forth kind of thing. Don't raise it up high enough, and it goes over top of the clamp, and there goes the tip of your bit. Not understanding the candle program and having to go through the G code. Okay, that was a really frustrating thing. This is the candle program, at least a part of the candle program, and that issue is kind of down here that I've got circled. And what happens is, after you finish with the mapping process and all that kind of stuff, and you got the G code is all loaded and ready to go, you hit that send button that I got in around that red circle. So the milling process starts, the spindle fires up and starts spinning, and then the machine goes to a safe position or a home position, and then it stops. And no matter what I did, I could not get the thing to start again. So I had to go through all the G code, because I figured, well, maybe there was something missing in the G code to tell it to carry on. One of our local hams here, Dave, VE3EAC, also has the same machine as I do, and he was doing some successful mills. So I got a sample of one of his codes and went through that. Didn't see anything of different that would help out there. And like I say, this is why this was spread out over several hours and over a few days to try and get this to work. And I can't remember how I came across it. And if and it certainly is not intuitive to me. And if it's intuitive to any of you guys, please let me know. But you see right here beside the send button, there's a pause button. Well, after you hit the send button and the machine goes to the home position, to get it to go again, you hit the pause button. Now, is it just me or is that intuitive? I don't think it is. Anyway, once I did that, away she went, everything's working. So days of frustration, all of a sudden, gone. Anyway, I certainly learned a lot about G-code. And here okay, once I started to really understand, once I stopped trying to mill the SC70 package size to start with and went to the larger sizes, now I could pay a little bit better attention and understand what was going on when I made the different settings with bit depths and passes, because you can take the angle of the V bits and calculate that into the depth and on and on and on. So like I say, once I stopped doing that, then things started to come together a little bit quicker. And once I get a little bit better handle on that, then I'll go back and see about milling that really small stuff. The other thing too is giving more thought to the the board layouts and pad and tray sizes. If you can go ahead with a larger pad size or tray size, then that's what you should probably do. And same thing with the pads, increase them a little bit if you can. Here, another thing that helps is put a piece of PCB behind the clamp, so that if you don't do that, then this will be on a bit of an angle, and that can, when you clamp down on it, you can kind of distort the board a little bit more. And again, this is just another shot of my setup for the clamp, or for the mapping process here. So this board here I put in, and I didn't give much thought about it until I went to go and mill it, and I realized the board's cut really the same size of where the some of the traces were going to be milled out, so I had no place to put the clamps. I managed to, if you look at the bottom picture, I just managed to put on a corner here, so that's how I did for the mapping process. So I put the clamp on here and then I mapped it out. But what I did instead was I put down the tape on both sides, on the spoil board and the milling board, or the PCB, and I put a ton of crazy glue down in between it and hoped that would hold. Of course, the other worry was I was also worried, can I get it back up again? I just wasn't sure which way it was going to go. But anyways, it held, never budged, and it came off pretty easy, much easier than I thought. Just a little bit of prime there, and then a bit of a scrape off, and it all kind of came off really good. So there's the board there that I've done. That board is now changed. I started, because this project was going, this is another story for another time, but here's actually where I started to use a breakout board, because I had a really small package that I was going to use in there. I've since changed my mind and I've redone the whole thing. I'm going to go with the original size package and not use a breakout board. And there's a couple other little things on this board that, now that I was really doing it, I changed it. Here's a closer look up to the corner here. And some of the things I changed was in here, you can see just a little bit, not quite perfect there, but you can see there's a lot of room in between. So what I've done is I went into KiCad and I changed the footprints a little bit, and I widened up the pads. And one of the things I started to do here, I don't think it shows very well here. It may not even be on this board. I've gone in with a larger trace, but what I've done now on the new board is I've widened up the hole, or the pad, and then I've come in on a wider trace. And then as soon as just before I get to the IC, I go down to a smaller size. I've also lengthened the pad out a bit to make the soldering a little bit easier. And again, if there's room in between here, then I've widened up the pad a little bit. And here's the you can kind of see here where that's where I've redone the board here, and you can see where I've come in with a thicker trace and then gone down to the size of the pad. These pads here I've widened up and lengthened them from the standard package. And there's just a shot of what I was doing with widening and lengthening the pads. You also have to change the size because as you make the pad longer, it kind of overhangs here. So you got to change the location to line it back up on the appropriate edge. These are just examples I found off the net. So takeaways I had was, like I say, use larger trace sizes, 0.7 or 0.8 if you can. It'll do smaller, but you know, if you can use the larger sizes, go with them. If you have room to, like I said, if you have room to widen the pads on those small chips, then do that. Consider areas for the clamps. Well, if you don't, then you're going to be required. Well, you need to do some hacksaw work and stuff like that, or you can continue on with tape and the glue method, which I think I might do. I also picked up some double-sided tape, and I'll try that next. Some time, learn the finer details with KiCad and flat cam. And I mentioned that because, and I just got down there, mill slots, drill holes, mill at the board. You can set it up where you can mill slots, you know, like for example, let me go back, like right here for the power supply connector. You know, it's got a slot in it. So to do that manually would be a pain in the neck. Well, get the CNC machine to do that. Of course, I have to learn how to do it. Drill holes, same thing. Any holes that are in there, well, change the bit on the milling machine and get it to drill it, so you don't have to do it manually. So those are some of the little details I have to still learn with between KiCad and whatnot. And again, milling out the board. So instead of taking your finished board, if it's off of a larger piece of PCB, and then you got to take a hacksaw and cut it out. Well, what you would do is you can tell the CNC to put tabs in it. And so up here, you might just have one tab here. You might put two tabs on the long sides. And then the program would go around the edge and mill out the whole board. So it would cut it right through, except for where your tabs are. And it wouldn't go completely through for the tabs to hold them in place, so that when it was finished, you could just pop them out. So that would save a lot of time from, you know, using the hacksaw method. And because that's a pain in the neck to do with a hacksaw. And that's it.
You've done a really tremendous job, Peter.
Oh, well, thank you.
That is a stunning bit of work. I remember when you started and the level of frustration that you had and some of the bits and pieces of wreckage. And I take a look at it now and it looks like it's picture perfect.
Well, the biggest frustration was trying to figure out the pause button was used to go.
Yeah.
That is a really, that's obviously an entry into the men's hut trick.
You know, there is a couple of videos. There's a few videos that can kind of help you with flat cam and whatnot, but there's not a ton of information like you can get for example, KiCad. So there is a little bit, but not a whole lot. And there's a lot of trial and error. And just don't be too ambitious at first. There's a lot of support groups out there as well. But if you're kind of looking for what's on the internet for the written word to help you out in videos, it's not quite up there. I'm not too sure who's first, but I guess Dave OOI.
Yeah, Peter, how do you set the origin? How do you tell it where to? Because everything's relative to a certain point, right? So because the reason I'm asking this is I'm trying to figure out how you could do a double-sided board. Because if you set the origin on the top side, flip it over, and you set the origin maybe at a couple points to make sure it's all relative, you should be able to mill double-sided boards.
Yeah, I haven't looked into that. I figured let me figure out the single side first. But yes, there is a way of doing double side. But the way you find the starting point is you manually bring the milling bit, the spindle, over to where you want to a starting point, and then you bring it down, and you'll have your two alligator clips attached to it, so that when your mill comes down, excuse me, and as soon as it touches the board, it now finds that that's its start point. And then everything is referenced to that particular point.
Can you have multiple start points? Because if you take your board, right, and you've just got one point, you flip it over, and if that board's rotated, it's going to be skewed, right? So,
I'm not sure, Dave. I haven't read into how they do it. Maybe you have to restart the set point again. I'm guessing.
Yeah, I don't. Yeah, I'm sure there's a way that it's interesting. You got that probe because I'm sure there's a way you could set various points. Just how it goes in and maps it.
Yeah.
There's probably some way of doing that.
Well, I'm sure there is a way. I might have even read something on it briefly, but because I wasn't worried about double-sided at that point in time, I didn't pay that close attention to it. You might even have to have a locator or something like that, a known point that you go back to and then reset the home point on the second side, I guess. I'm not sure.
Yeah, it's cool. This has got a ton of potential.
Oh, yeah.
Thanks.
Dave, DAC. You had a question?
Sorry about that. No, I'm good to go. I just thanks for showing us that. If I got my hand, I didn't put my hand up on screen. Did I know it?
Oh, you know what? You're right at the spot where it's telling me there's 3 hands up at the moment, and I thought,
okay,
it was yours. Okay, no worries.
No, good stuff. Appreciate it.
Okay, Dwayne, you're up next.
All right, yeah, I've got just about the same kind of a similar setup as that. For double-sided boards, normally what they'll do is go and drill a couple of pilot holes on the board. It's going to be out of place, like if they're going to be mounting holes or something for the board. Drill that into the backer board and put some pins in there. So when you go and swap it around, you can maintain the same set point. And then when you're using your flat cam, you go and either set the thing up either mirrored or unmirrored, or actually you have to do that in the Gerber files. The hardest problem I find with using it is getting the width of the trace of the cut, because it's so dependent upon what type of bit you've got, what depth you're trying to do. Sometimes you're using different weight copper and stuff like that.
I know what you're saying there, Dwayne, with the V, like there's a 20-degree bit and 30-degree V bits, and then
yeah,
flat cam, you got that calculator to for the new depth because of the V and all this kind of nonsense, and then when you're going through it, I've noticed that between that and the videos I watched, it was starting to get confusing. So I started to use the even though I was using a V bit, I wasn't using the V bit selection. And trial and error, you get comfortable for the depth that you want to cut at. I can't remember what I'm cutting, that 0.007 or something. I can't remember. Anyway, but you get comfortable with that particular setting. Whether it's the right way to do it, I don't know, but it's working for me.
Yeah, I mean, it's the problem I've had with it is consistency. This is something I'm not sure if you can see the board I laid out and routed this afternoon.
Oh, yes.
I haven't gone and put it together yet. I'm going to have to make another one because I've got some problems with spacing and stuff like that. But it's basically a little BFO with a 5351 module and a little OLED display. I found out for most of the things that I can do better just using it to drill the holes, cut the board out, and then basically I'll go and use the toner transfer and put the put that onto the cutout board with the holes and go and etch it. Especially when I've gone to surface mount devices like there, it's much more consistent, especially with smaller things. And one thing I've also been playing with the other day is surface mount. Unless I go and make a solder mask for it, trying to get the right amount of solder paste on there, it is really a pain. And I played around with it just the other day, making solder paste templates to make life a whole lot easier.
Okay. Well, that's interesting. I haven't contemplated that one yet. Of course, one step at a time. Get the PCB boards down first and then worry about the solder mask. Okay. Thanks, Dwayne. What we got next here? Al, you're up next.
Great presentation, Peter. I enjoyed that tremendously. Just a quick question on what software came with your machine. I see you're referring to what, FlatCam and Candel. Are these included? Are they like a 1-year license or
I think Candle came with it, and I can't recall whether if FlatCam came with it or I just downloaded FlatCam and they recommended it. I'm not sure which, but either way, they're both free.
Okay, great.
Yeah. Drew.
Yeah, I just had one question. Is there a setting in your Gerber software, whichever software you're using to generate the G code, that has a change tool designation so that you can have the machine pause and go to a spot where you can change the tool, say to drill holes in or widen the grooves it's cutting, that sort of thing?
Yes, that's in FlatCam.
Is it fairly easy to do?
Don't know, haven't tried it yet.
Okay, just thought I'd ask because that's one thing
I know it's there. I just haven't done it yet. I was really trying to get the board down to producing the board because I wanted to get this project of mine finished. So of course I thought, well, I have minimal amount of holes on this particular board, so whatever is there, I'll do it by hand. But I know going forward, I'm going to have to do something along that regard.
Yeah. Okay, thanks.
Howard, you're up next.
Yeah, hi, Peter. Enjoyed the presentation. Just a quick question. Does it have like a simulation mode where it'll run through the program but not actually do the etching so you can kind of check to see that you programmed it correctly, or do you just have to go and if it works, it works?
I don't know if it has a simulation. I don't know about that. I think it estimates how long it's going to take you. No, I don't even think it does that. I'm not sure. I don't think so, Howard. I think you got
one.
Sorry, what was that, Dwayne?
Yeah, Candle actually has one, but basically it runs through it real fast and it only goes and checks for errors.
Yeah.
Oh, I was just trying to think of a way to avoid, like, if you get halfway through it and realize there was a mistake.
Well, no, you know what? When you're using KiCad, you got to make sure everything's right. Because once you've downloaded and you're going, it's going. The only thing that could go really would go, assuming that your KiCad work is correct, then everything else is going to be correct. And then when you're in FlatCam, you can double check it in FlatCam because all the traces and everything will all be visible to you. And if you do have to make some changes to it, you can do that through FlatCam. You don't have to go back to KiCad, I believe. But I haven't done that yet to try it out to see how it works.
Yeah, interesting. Thanks.
Okay. Cherry, good evening. Cherry, you had your hand up? You're muted.
I can hear you, Cherry.
Huh. I can't hear Cherry. Do you know what Cherry said, Drew?
Well, all I heard was he was checking. He said he's using a Raspberry Pi for his network. Cherry, Cherry, can you,
he's still showing it for me. Okay, well, let Cherry see if we can figure out what's going on there, and I'll go over to Dave. Dave DAC had a question. Oh, he's not even there now.
Yeah, Dave checked out.
Oh, he checked out. Oh, well. Okay. Any other questions? Okay. Does anybody else have anything else to comment on or questions or what have you? Okay. Well, hearing none, I guess that's... Oh. Yeah, I would say so, Cherry. Oh, you're welcome. Yeah, I guess that's it for tonight then, everybody. Thanks, everybody, for joining. I think we had up to about 16 at one point, which is great to see. And I thank everybody again for coming out and joining us, and look forward to seeing you at our mixer next month.
Oh, very good. Sound effects. It was very good, Peter. Thanks.
Okay.
Good night, all.
How'd you like it? And the record. Where's Eric? There he is.
Yeah, thanks, Peter.
Off, Eric. Oh, Dave, you know what? I forgot you were going to say something. I can't hear you.
I said it doesn't matter. I'm not important.
Yeah, but you didn't hold your hand up. I gave you the opportunity. I can't.
No, I just said I got a teaser in case you were short to me. That's fine. No, it's okay. No worries, man.
Is it